Okay, so let's finish up C13 spectroscopy for the semester. Oops, that's right, I don't need this anymore. Don't need my mask. All right, so Dept, we call it Dept, NMR, DEPT. It stands for distortionless enhancement by polarization transfer. Nobody ever says all of those words. They just say Dept. And so when you think about depth spectroscopy, it is a type of experiment in C13. So all the rules that hold true for a C13 spectrum hold true for a depth spectrum, right? So the number of carbons, well, we'll talk about the number of carbons, but certainly the chemical shift, right? So the chemical shifts that you've learned for carbons doesn't change when you look at a depth spectrum. What a depth spectrum does for you that a C13 does not is that a depth spectrum actually can tell you whether a peak you see in the C13, whether that is a CH3 group or a CH2 group or CH or a carbon with no hydrogens, right? That's the valuable information you can get from looking at a depth spectrum. That said, you have to run a C13 spectrum first so that you know how many peaks there are and where those peaks show up. And then after that, you run a depth spectrum, or you collect a depth spectrum, and then you get further information about those peaks. And so when you come in to use the NMR, we will first run a C13, and then we'll run a depth, so you'll have both of those pieces of information to go forward. And the reason you need to run a depth is because when you think about the products of your reaction, and this is where I'm going to ask you to pause the video in a minute, right? I want you to look at, if you did experiment B, look at the two possible products and tell me how many carbons you would expect to see. If you formed the first molecule, how many carbons would you expect to see? And if you formed the second molecule, how many carbons would you expect to see? And if you're going to run sample or experiment C, do the same thing, right? In the first picture that I drew for you, how many carbons would you see in the NMR if you made that product? And then look at the second one. How many carbons would you see in the NMR if you made that product? Right? So go ahead and pause the video and figure that out. So I'm not going to tell you the answer to that, right? But ideally what you saw, so if product 1 and product 2 formed two different numbers of peaks, right? If your first one formed, and this is obviously it's not going to be 16, but say you said the first one was 16 and the second one was 17, right? If those two products differ by the number of carbons you could see in the NMR spectrum, then all you would have to do is run an NMR spectrum, right? And count your carbons. And if you had 16, it would be this one, and if you had 17, it would be this one, right? But if you look, you should notice that both of the products in B or C, right, they form the same number of carbons. And so just looking at a C13 spectrum would not tell you which of those two products you made. So now we have to look at depth spectrum. And it turns out that there are three different, when you say you're going to run a depth spectrum, there are actually three different depth spectra that get collected. And we call them Dept 90, Dept 45, Dept 90, and Dept 135, right? And so you don't get to pick and choose. The instrument just runs all three of these for you, and you get the data from that. And so you've run a C13 already, and so now you get this information. And so the peaks that you will see in a Dept 45, the carbon peaks that you will see are carbons that have 3 hydrogens, carbons that have 2 hydrogens, and carbons that have one hydrogen. And so what you don't see in a Dept 45, and what you don't see in any of the Dept spectra, are carbons that have no hydrogens, right? That just has to do with, you know, all of the theory and the technology that we skipped, rightfully so, to get here, okay? So you have to run a C13 spectrum first, because in a C13 spectrum, if you have carbons that don't have any hydrogens, they'll still show up. And so when you compare your regular C13 spectrum to a Dept 45, if there are peaks that are missing, right, they were present in the C13, they're not in the Dept 45, that tells you that that carbon that's missing, those peaks that are missing, that tells you that those carbons have no hydrogens on them. So that's the value of a Dept 45. Again, the chemical shifts for all of the peaks here will be exactly the same as they are in a C13. So you can just match them up and see which peaks are missing. Now, what does a Dept 90 tell you? A Dept 90 tells you or shows you carbons that have one hydrogen. So when you look at a Dept 90 spectrum, you're only going to see peaks from carbons in your molecule that have one hydrogen bound to them. You won't see anything else. And in a Dept 135, you will see carbons with 3 hydrogens and carbons with 1 hydrogen pointed in the positive direction, pointed above the axis. And you will see carbons with 2 hydrogens pointed below the axis. So any carbon in your molecule that is a CH or a CH3, that'll be pointed up. Any carbon in your molecule that's a CH2 that has 2 hydrogens on it, that'll be pointed below the axis. Okay? Again, chemical shift the same. So really, you can see in all of the Dept spectra that if you have a carbon with no hydrogens on it, it just simply doesn't show up. And so that's why you need to compare it to the C13. And then do you really need a Dept? The truth of that is no. But our instrument runs it, so you're going to get one, right? Because if you have a Dept 90 and a Dept 135, then you can compare these two spectra, and you know when what you're seeing above the axis are CH3 and CH groups, but you only see CH here. So you can easily figure out which one of these peaks that you're seeing above the axis are CHs when you compare it to the Dept 90. So then you also know which carbons are CH3. And then you know which carbons are CH2 because they're below the axis. And then you know which carbons don't have any hydrogens because they don't even show up. Okay? So if you manipulate a C13 spectrum and a Dept 90 spectrum and a Dept 135 spectrum, you'll easily be able to figure out which of the carbons in your molecules have how many hydrogens on them. Again, if you're trying to build a molecule from scratch when you don't really know anything about it, collect the spectra, excuse me, then you'll know a lot more. Okay? So an example and I'll go ahead and post this example for you. So if you haven't printed it out, go ahead and print it out. This is a molecule called ipsenol. Okay. And what I have for you is the C13 spectrum on the bottom, and then the Dept 135 in the middle, and then the Dept 90 on the top. And so what you can see in the middle is that you have peaks that go up and you have peaks that go down, right? Up and some down, right? And so you can see that the chemical shifts all match up with your C13. So I know from my C13 that this peak, bad choice. I know from my C13 that these two peaks are CH2. This is a CH2 and this is a CH2. And I know that because they're pointed down in my 135. and these two peaks are CH2s. And what I know out here, closely, right? What I know out here is that this is my Dept 90, so I know this is a CH. So I know this is a CH. So I know this is a CH. And this peak doesn't show up anywhere, so I know this is a carbon with no hydrogens. So that's a carbon with no hydrogens, which we call a quaternary carbon. This is a CH because I see it here. These two are CH2s. This one is a CH, right? This is a CH because I see it up here. And then CH2s. And then one of these, again, you have to line them up. But one of these is a CH and the other is a CH3, right? So when I look at this spectrum and this spectrum, CH, CH, I'll say these two, right? RCH, and then this one must then be a CH3 because I see it in the Dept 135, but I don't see it in the 90. And so what you're going to need to do, the reason you're going to need to use this Dept information is because you found out by looking at the structures of your molecules that you formed in this experiment, or that you will form in this experiment, right, that they have the same number of carbons. So just simply running a C13 isn't going to be enough. And so now you have to go through each one of your molecules and say, okay, for this first molecule, in a Dept 45, look at its structure. In a Dept 45, how many peaks will I see in the Dept 45? And then if I run a Dept 90, how many peaks will I see in the Dept 90 of that structure? And if I see run a Dept 135, how many peaks will I see in the positive direction? How many peaks will I see in the negative direction? And then do that same analysis for the second molecule. And you're going to start to see that it's in the Dept areas that those two molecules are going to differ. And therefore, when you go ahead and collect your spectra, you will then be able to determine which of those two molecules you have because you have actual Dept NMR data that will match up with what your expectations are. All right. All of this information is in your textbook. You can read those pages and get all that information there. I will, of course, answer any questions that you have. You have all of the videos or all of the pages from the C13 analysis in your notebook or in your lab manual. I will go ahead and post this picture for you on Blackboard just so that you can see what really a Dept 135 looks different because peaks are above and peaks are below. And so that's just something different for you to see. And other than that, think about how all of this C13 and Dept information applies to the lab that you did so that you can ultimately figure out which one of those products you ultimately make. So, good luck. Ask me questions. I know it is confusing. It's the first time you're thinking about this kind of stuff. The sooner you think about this, the sooner you ask questions, the sooner we can fix the little pieces that might not be fitting into place right, and then you will be perfect NMR spectroscopists. All right, see ya.